All right, now that the last lesson allowed us to simplify square roots so that we can get them out down to a common, to its lowest square root kind of value, now to add them and subtract them, they have to be exactly the same. They have, so like a square root of 24 and a square root of 24, those will go together. This is very similar to negative 2, and then I'm just going to call this x minus 2x. See, those go together to become negative 4x. That's how square roots work too. They have to be exactly the same thing. So a negative 2 square roots of 24, notice that the x doesn't change. That's a thing and that's a thing, so we're adding up things and it stays the same thing. Okay, so this is going to be negative 4 square roots of 24. So I have negative 4 of these things. Now, before I go and put a box around that, I have to make sure that 24 itself does not have a perfect square in it, which it does. 24 has an 8 in it, or let's see, it has a 4 in it. I don't care about 8. 8's not a perfect square. It has a 4 in it. So I'm going to rewrite that as negative 4 square roots of 4 times 6. And the square root of 4 is 2. So on the outside, I have negative 4 times 2, so we end up with negative 8, and then on the inside, we have the square root of 6. So those things add up to something that looks like a 24, but then we had to simplify the 24. All right, only things that are the same can go together. So here I have 3 square roots of 18, and there's 3 square roots of 18. Well, one's positive, one negative. That adds up to 0. So the only thing left there is 3 square roots of 2. Now that was not a very good example. What if it was 3 square roots of 18 minus 4 square roots of 18 plus 3 square roots of 2? I'm going to change this problem just a little bit so those just don't go to 0. What you usually need to do, what's the best thing to do is to get it simplified first. See, the square root of 18 is really the square root of 9 times 2, which breaks that out as a 3. And there was already a 3 out there. So really what this whole thing was a 3 times a 3. It was really 9, and then that square root of 2 was left in there. Same thing happens with this 18. It was 9 times 2. The 9 can break out as a 3. So what's out there is 3 times 4, which is 12 square roots of 2. And then we have 3 square roots of 2. See, they were really all square roots of 2 in the first place. Okay, now we can add them together. So I have 9 of them minus 12 of them plus 3 of them. Then the whole thing would just be nothing. Let's just pretend this was a 4 square roots of 2. Then it would be 9 of them minus 12 of them plus 1 of them. Then it would be 1 square roots of 2. Okay, third roots are the same thing. We want to get it simplified down all the way first. So looking for third numbers. Remember, 1 to the 2 to the third. So I'm looking for 8s. Well, 81 is not going to be divisible by 8. 3 to the third is 27. Okay, well, 81 is divisible by 27, so I'm going to break that down like that. So I have 2 third roots of 3 times 27 minus a third root of, okay, 16 has an 8 in it, so I'm going to call that 2 times 8, and then plus the 3 third roots of 2. Okay, see the third root of 27, that's really 3 times 3 times 3. That breaks out of there as a 3. So what I have out here is 3 times 2, so that's a 6 third roots of 3. This 8 is really a 2, 2, 2, so that breaks out as a 2. So here I have 2 third roots of 2. And then out here I have 3 third roots of 2. Okay, these two can go together because they're both a third root of 2. These are the same. This one is not the same. So this one's as it is. So this one stays 6 third roots of 3. And then here's a negative group, negative 2 of them and a positive 3 of them for a grand total of positive 1 of those third roots of 2. Okay, so we have 6 third roots of 3 plus 1 third roots of 2. Okay, well the nice thing over here is that's simplified. There's no 3 pieces that will make a 6 or a 4 or a 6, so those are all good. Actually, this one is not. I'm going to fix that one. And then the 108, I'm looking for some third roots of that. I think there's a 27 in 108. 108 divided by 27 is 4. Okay, so I could rewrite this one as -3 third roots of 27 times 4. See, I like 27 because that will come out as a 3. Minus 3 third roots of 6. Nothing's going to make a 6. Minus 3 third roots of 4. Okay, I do want this one to change. The 6 isn't in there, but I am going to change this one to -3 third roots of -1 times 6. Okay, now I said in third roots that we don't ever use the 1, but that's not true. 1 to the third is 1, as -1 to the third is -1. So 1 actually is going to be useful. The third root of -1 is still -1. What that means is I can take that -1 and put it on the outside so that it's not imaginary. And here I can take this 3, 3, 3. This is really a 3, 3, 3. I can take that package and put it on the outside as a single 3. So here on the outside I've got 3 times -3, so I've got -9 third roots of 4. Here, this one, nothing happened, so it's 3 third roots of 6. Here I have -3 third roots of 4. And here I have -3 times -1, so that makes it +3 third roots of 6. Okay, those two are third roots of 6. They'll add together. So I've got -3 of them and +3 of them, so they actually add up to 0. But then this group, there's a group of 3 roots of 4, and here's a group of 3 roots of 4. So -9 of them and -3 of them is -12 of those 3 roots of 4, and the roots of 6 went to 0. Okay, so that's adding and subtracting. You got to get the base root the same, and then you can just count them up. So that's add and subtract. Multiply. It is okay to multiply square roots. See, really, this means you can put it all under one hut. There's a rule that says, okay, square roots, if it's multiply, they just all belong under one thing, so this is the square root of 6. It really is that simple. So square roots do multiply. They have to be the same in order to add, but then they do multiply. And then, when you add them, they don't change the square root deal, but here they change the square root base. Okay, so to put the 15 in there, that's just the square root of 15 times 5. What's 15 times 5? 75. So that becomes the square root of 75 minus, now, the way you do it this way is everything on the outside multiplies, the real parts multiply, and then the radical parts multiply. So there's an implied 1 there. So 1 times -5 is -5, and then the root 15 times the root 3 is root 45. Now those are not the same, so they cannot add, but they have perfect squares in them. See, 75 is really 25 times 3, and 45 is really 9 times 5. Okay, here the 25 can come out as a single 5. So that leaves 5 square roots of 3. And here the 9 can come out as a 3. The square root of 9 is 3. So 3 times 5 is -15 with the square root of 5. Now those still are not the like terms, so they still don't go together. So now it's finished. Okay, a 6th power. That means we need something to the 6th. Okay, that's getting kind of crazy. 2 to the 6th. Let me check and see what 2 to the 6th is. What am I even going to look for? 2 to the 6th is 64. I'm pretty sure 512 will divide by 64. Yes, it will divide by 8. So 512 is 64 times 8, and 64 is 6 packages of 2s. So this is the 6th root of 64 times 8 times, okay, 32, see that 2 is the smallest one we got, and it's already more than that, so that's not going to do anything. So times -4 sixth root of 32. Okay, this 64 is a 2, 2, 2, 2, 2, 2. So see that 64 comes out of there as a 2. So what we really have is 2 sixth roots of 8 times -4 sixth roots of 32. Okay, well 2 times -4 is -8, so that's what's on the outside, and then 8 times 32, the inside is 256. Now that worries me a little bit because I think that might have a 64 in it. 256, sure enough, does have that. So 256 still needs to be simplified now. 256 is 64 times 4. And again, that 64 is a perfect sixth. That means it's a 2, 2, 2, 2, 2, 2. That's really what 64 is. So that whole package can come out as a 2. So on the outside, I have 2 times -8 for -16, and on the inside, we have the sixth root of 4. All right, division works the same way. You can just put it all under the same. Sometimes you like to have them separated, and sometimes you don't. See, this could be the square root of 3/4. But that's not really helping, because what I really want to see is, okay, the square root of 4 is already just the number 2. So this simplifies to the square root of 3 on the top, nothing can happen there, and then an actual 2 on the bottom. And that's how those look. Now for square roots, for fractions, you don't want to have a square root on the bottom. So if there were a square root on the bottom, we would fix it like we did in some videos before. Okay, so that's what's got to happen here. Well, this one, I want to show you two things. First of all, I know there's a couple ways to do this right off the bat. The square root of 4 is 2. So probably the simplest way is that's already just a 2. So the bottom is 2 times 2. So this is 4 minus 4 roots of 2 over 4. Now, I want to do a thinking bubble here. If I have 2 plus 3 over 2, okay, we know that we can see that that's 5 halves. That has to be 5 over 2. Okay, can I just cancel this 2 and this 2? Okay, well that makes 3. That is not 5 halves like we already knew it was. Or 2 divides into itself once and into itself once. Now it's 1 plus 3 is 4 and over 1. See, those are not the same thing. That's not a legal cancel. So you cannot cancel just part of it. Like that 4 and that 4 will not cancel out, because here's the real example. This has to be 5 halves, and if we cancel those 2's out, it's not. What about 2 plus 4 over 2? So we know that answer has to be 6 halves, or 3. Okay, well, if I cancel this one down to a 1 and this one down to a 1, now I have 5 over 1. That's not 3. But if I cancel that by a 2 and that by a 2 and that by a 2, now on the top I have 3 and the bottom I have 1. That equals 3 over 1, which is still 3. See, if you're going to cancel on a mixed fraction like this, it has to cancel everywhere. Now really, this is what we're doing when we have 2 plus 4 over 2. The math is really, you got to factor something out of the top. If I factor a 2 out of the top, that leaves 1 plus 2 over 2. It's really the factors that cancel out, which makes the 3. So the concept is, on the top there's a 4. I have a 4 that I can factor out. 4 divided by 4 is 1. That 4 divided by 4 is 1 square roots of 2. And now the multipliers cancel out, and that's the answer, 1 minus the square root of 2. Okay, but most people, for speed, do it this way. As long as you can reduce it everywhere, you can reduce it. Reduce it by 4, reduce it by 4, reduce it by 4, and see that's now still 1 minus the square root of 2 over 1, which is the same thing as we had. So as long as you reduce it everywhere, that's the shortcut for factoring and reducing the factor. Okay, the problem with 10 is it has a square root on the bottom, so we have to use that conjugate that we were doing one other time. Remember, the conjugate is the same numbers minus the square root. So up here we'll do 4 minus the square root of 3, and then you just multiply the whole thing together. 4 times 4 on the bottom there is 16. 4 times minus square root of 3 is minus 4 square roots of 3. And then I'll do it here. That's square root of 3 times positive 4. This right here is how come it always works, because that makes the middle term always go to 0. And now square root of 3 times the square root of 3 is the square root of 9, which is 3 with 1 negative, so it's minus 3. See, the bottom turned into a whole number, 19, or 13. Then the top, we'll just multiply this together. So that will be 4 square roots of 2, and then square root of 2 times square root of 3 is square root of 6, and that will not simplify. So our final answer to that one is 4 square roots of 2 minus the square root of 6 all over 13. Now that's considered simplified because the bottom does not have a square root in it. Okay, we don't care about the top, we only care about the bottom. So the conjugate here is 4 minus the square root of 2. Okay, the bottom, 4 times 4 is 16. See, this is negative 4 square roots of 2, and this is positive 4 square roots of 2. So I'm not even going to write that down. And then square root of 2 times negative square root of 2 is negative 2. So the bottom became 14. The top, however, is going to be 2 times 4 is 8. 2 times that is negative 2 square roots of 2. Okay, these two together, 4 times 4 is 16 square roots of 5. And now this one, you just the outsides together, so 4 times negative 1, so negative 4. And then square root of 5 times square root of 2 is square root of 10. Now I'd look at that to simplify, which it does not, so I'm good. None of them go together. A 2, a 5, and a 10 will not go together, so that's the answer to the top. So the top is 8 minus 2 roots of 2 plus 16 roots of 5 minus 4 roots of 10. That's as simplified as the top can get, all over 14. And that's considered simplified. I know it looks more complicated than when it started, but the bottom has no square root in it. Okay, if there's no addition, then we can just multiply it by its own self, because the square root of 3 times the square root of 3 is just 3. And now the top is going to be 5 square roots of 12. So we're all golden, but the 12 has a perfect square in it. So that's really 5 times 4 times 3. See, there's the 12, and the 4 is going to break out all over this 3. So the top is 5 times 2. So outside we have 10. On the inside we have square root of 3. On the bottom we have a 3. Those 3's are different. This is a square root. This is a real. They're not related. Those two could reduce if they could. If that would have been a 9, we would have reduced those there. But since it's not, that's simplified. So number 13, I'm going to change colors just so it doesn't bleed into that one. And all I need is a square root of 2. Because square root of 2 times square root of 2 is 2. And I'm going to take it times that one. So that's 3 square roots of 2. And then take it times that one. Square root of 10. Now sometimes, okay, I said it before, if you can reduce everywhere, you can reduce. So 2, 2, and 2. We can divide by 2, divide by 2, divide by 2. But that's a no-no, because this is a real 2, and these are root 2's. Those do not reduce one another. It's only the real parts that can reduce, so that one is done. Okay, down here, I think I'm going to fix this first, because the square root of a p to the 4, I can make that smaller. Remember, that p to the 4 is like a group of p's there that can come out, and another group of p's there that can come out. So those p's are not even in there. And the same thing here. There's 2 p's that can come out, and then there's 2 more that can come out. So just to get started, I'm going to rewrite it. I have this 5p squared that I didn't do anything to, But now I have a 5p squared with the square root of just a 3 left, because I took all the p's out. Worked out just so they all came out of there. And in the bottom, I've got 4p squared on the bottom, and then what's left on the inside is the 11. Now, I was saying that if you can reduce all of them by the same thing, you can do that. Okay, this one has a p squared. This is one piece. It's one piece because it's all multiplied together, so it's called a term. So this term has a p squared, this term has a p squared, and this term has a p squared. I can divide a p squared out of everybody. So really, before we even get started, it'll make it simpler if we call this 5 plus 5 roots of 3 over 4 roots of 11. Now, I don't need the root, I don't need to care about the 4, that's fine. It's only the root 11 that's the problem here, so I'm just going to multiply by root 11. See, these two become 11, so the 4 is already out there, and then there's an 11, so the bottom becomes 44. The top is 5 square roots of 11 from that one, and this makes the square root of 33, so it's plus 5 roots of 33. Can't simplify that or that, so the whole thing becomes 5 roots of 11 plus 5 roots of 33 all over 44. Now the 11, 33 are roots, the 44 is a real, so those do not simplify any more than that. If this would have been a 45, I could have reduced all of the 5s. I could have reduced it down by a 5. But it's not, so that's it.